Welcome everyone to section 6.6, Integration by Substitution. This is our very last lecture for our summer class. I don't know if you can believe it. I can hardly believe it. This video is going to be a little bit long, so just hang in there with me. All right, we're going to tackle integration by substitution together. So first we're going to do a little bit of a warm-up, and we want to recall compositions of functions. All right, so for the below questions, we want to find f of x and g of x such that h of x is equal to the composition f of g of x. All right, so we have part A, we're given h of x, and we want to find the f of x and g of x that can create h of x. Okay, so basically we're looking for the inside and the outside functions. Kind of think about the chain rule, our compositions of functions, things like that. So here in our first part, we're going to take our exponent, x cubed, and we're going to make that our inside function. All right, so then our outside function will be f of x, and that's going to be 3e to the x. So when we put this together, when we have f of g of x, which is x cubed, we put an x cubed everywhere we see x, and we end up with 3e to the x cubed, which is in fact our h of x. All right, let's do part B. Again, we're looking for an inside function. Here we're going to pick what's inside our natural log. So g of x will be our inside function, which will be 5x plus 7. Our outside function, f of x, is going to simply be 2 times the natural log of x. Again, this way we can put f of this g of x function, 5x plus 7, and so we get 2 times the natural log of 5x plus 7, which is our h of x again. Lastly, we have part C. Here, our inside function is almost everything. It's our 2x squared plus 1. So our inside function is everything inside of our square root, and then our outside function is simply the square root. Okay? So again, we have f of 2x squared plus 1, and that's going to give us our square root of 2x squared plus 1, which is our h of x again. So we already learned how important inside and outside functions are when we've talked about things like the chain rule. All right, so now that we have moved into antiderivatives and integrals, we need a way to handle something like inside and outside functions. All right, so this is where u substitution comes into play. All right, so let's say we have the integral of a composition of functions. So f of g of x, and let's say that's also multiplied by the derivative of g of x, dx. All right, so we want to make a substitution. So we want to let u, this letter u, this is why we call it u substitution, but you can use whatever letter you would like, it's just typically the u. All right, so let u equal the inside function, g of x. Okay, so if you remember, we need to have all of the same variable inside of our function. All right, in our last section, we talked about needing everything in terms of p equals, so in terms of q. All right, that's because we were trying to take the integral with respect to q, and all the variables have to match. Okay, so if we say let u equal g of x, so basically we're going to plug in u for everywhere we see a g of x. So we just get f of u times g prime of x dx. All right, so now we have mixed variables. We have a u in there with an x, and we're trying to take the integral with respect to x, so that's not going to work. We need to do one more thing. So when we make our substitution, u equals g of x, we also want to take the derivative of this. All right, so we're going to get the derivative of u with respect to x is equal to g prime of x. All right? And then we're going to do one more thing, which we've said when we first learned about Leibniz notation, is that this du over dx is not supposed to be treated like a fraction. All right? However, we're going to make a small little exception in this case. All right? And just hang in there for a second. So we're going to say that we can write this as du is equal to g prime of x dx. And the reason we're doing that is so that it's easier for us to see how we can substitute this in. All right, so we can take our g prime of x dx and our g prime of x dx and substitute du. All right, so we're going to end up with f of u du, and that's it. So the act of doing a u substitution is taking us from here to here, and basically simplifying our integral so that we actually can take the integral. Okay? So let's go ahead and look at a few examples. So for example 1, again, we're just trying to use u substitution to find these antiderivatives. All right, so we want the integral of the square root of the natural log of x over x with respect to x. All right, and picking the best u is not always intuitive, okay? It takes a little bit of trial and error to start, but really it's knowing where is our inside and outside functions and trying to think that way. Also, trying to think ahead and looking to see if we take the derivative of u, do we have that derivative there? Do we already have it there? All right, so in this case, I'm going to pick the inside function, that's going to be our u. So I'm going to pick the inside function, that's our natural log of x. All right, so I'm going to let u be equal to my natural log of x. But we need to take the derivative so that we have that also. All right, so we have the derivative of u with respect to x. The derivative of the natural log of x is 1 over x. All right, so then we move the dx over, we get 1 over x dx. And if we rewrite our integral, we could write this as 1 over x times the natural log, times the square root of the natural log of x dx. So we have 1 over x dx, and we have a little squiggly there, 1 over x dx. All right, so we have the integral. Our square root of the natural log of x becomes the square root of u, because we're doing our substitution here. All right. And then our 1 over x dx becomes our du. Okay? So we just end up with the square root of u du. And that is something that we can handle, right? We know how to take this integral. Before, the whole square root of the natural log, a quotient, we don't have a quotient rule for an integral, right? So that's why we need this u substitution technique. So let's go ahead and rewrite the square root of u as u to the 1/2 du. And we can go ahead and take this integral using our power rule for integrals. All right, so it's going to be u to the 3/2 because we increase the exponent by 1. And then we divide by the exponent, but it's a fraction, so we're going to flip and multiply. So 2/3 u to the 3/2. All right. But then we need to add our constant of integration. So we're not done yet. All right, and we're still not done because we started off in terms of x, but we need our answer in terms of x because so far we're in terms of u. All right, so we said u was equal to the natural log of x. So we're going to do what we call back sub, which is essentially undoing the substitution that we made earlier. All right, and we're going to replace u with the natural log of x. So we have 2/3 times the natural log of x to the 3/2, and we still need to carry down our constant of integration, and that is our final answer. All right, so that's our first example of using u substitution to calculate, in this case, an indefinite integral. We're going to do a lot more, so if that one was a little bit confusing, don't worry, okay? Let's look at part B. So in this case, we have the integral from the integral of 2x over x squared plus 4 dx. All right. And in this case, there's not really an inside or outside function. So if that's not really what we have going on, the next best thing to look for is the most complicated, I'm putting that in air quotes, the most complicated piece. Because we are going to take the derivative of it, and that should simplify it, right? So in this case, is 2x more complicated than x squared plus 4, or the other way around? This might be a subjective question, okay, which is kind of why I put it in quotations here. I'm going to say we want to let u be equal to this x squared plus 4. All right. So if we take the derivative, we end up with 2x, right? The derivative of a constant is 0. Use our power rule. So we get 2x. Well, that works out well because we have a 2x right up here, don't we? All right, so then we get du is this 2x dx, which we have right there. So this becomes our du. And we're going to substitute this x squared plus 4 for u. So this ends up being 1 over u du. It's amazing how much simpler our integral can look after doing u substitution, isn't it? The integral of 1 over u, we know that's our natural log. So it's our natural log of the absolute value of u. And then we need our plus the constant of integration, okay? And we still need to back sub. We still need to get back into the original terms. This is going to be very important when typing in your answers online. You always have to remember to put them in the correct variable. All right, so remember that we still need to back sub. to give us the natural log of the absolute value of x squared plus 4 plus c. And there is our final answer. All right, so let's move on to example 2, where we just are going to calculate some more integrals. Okay, this is a pretty similar part to one of our composition warm-up problems, where we want our inside function to be our exponent. Okay, so we're going to let u be equal to our x squared. Remember, we need to take the derivative, so du dx is equal to 2x, and then we'll move our dx over. So du is equal to 2x dx. All right, so again, our 2x dx is found here, and we're going to substitute u in for x squared. So all we end up with is the integral of e to the u with respect to u. Again, making sure our variables always match up. We should never have x's and u's mixed together, all right, in an integral. So our our integral of e to the u is just e to the u, right? E to the u. And then plus c, because we're dealing with an indefinite integral. And lastly, we need to back sub. So we have e to the x squared plus c, and that's it. All right, let's do another one. Here we have 2 binomials, or really we have 10 of them because this one's to the 9th power. All right, so sometimes it's worthwhile to go ahead and multiply these out, because if you don't need to do a u substitution, then it could be a bit simpler. However, I don't know about you, if you want to, go for it. I don't really feel like multiplying out 9 of these. Okay, so instead we are going to use a u substitution. And we want it to be inside of whatever we're raising to the 9th, because that seems to be the troublemaker here. All right, so we want u to be 4x squared plus x. All right, so when we take our derivative of u, we're going to get 2 times 4, which is 8x, and then the derivative of x is 1. So we have du is equal to 8x plus 1 dx. All right, so this is our du is right here. And our u is going to be everything inside of what we're raising to the 9th. All right, so this is going to become u to the 9th du. So now we have a power rule integral where we need to add 1 to the exponent and then divide by that new exponent, and then plus c for our constant of integration. And then we need to back sub. So we need 4x squared plus x raised to the 10th power, all divided by 10 plus c. And that is our final answer. All right, about here in an in-person class is when I'd be asking who's feeling overwhelmed. All right, so if that is you, feel free to pause the video, try to look over the questions again, send me an email. I do have 2 more sets of office hours before our final exam, so please come to them if you need any help. Otherwise, we're going to keep powering through with a lot more examples for you. All right, so part C, We have a really big fraction going on. All right, so like I mentioned in one of our previous examples, we want to pick perhaps what looks the most complicated to be our u. All right, so we want to let u be equal to everything that's under that square root. All right, we want all of that. So we want 2x squared minus x plus 7. We want all of that to be our u substitution. Plus, if we look one step ahead, it looks like we have the perfect derivative already lined up for us. All right, so du dx is equal to 4x minus 1. And so move the dx over, and we have 4x minus 1 dx. And sure enough, that's what we have. All right, so this is our du, is this and this. And our u is everything that was inside our square root. Okay, so our integral simplifies down to 1 over the square root of u du. So let's go ahead and rewrite the inside of our integral. First, I want to write our exponent as 1/2. So we have the square root, I want to write it as 1/2. And then I'd like to bring it up to the numerator. So I'm going to have u to the negative 1/2 du. Well, now I can use our power rule for integrals. Right, so we add 1 to the exponent, so negative 1/2 plus 1 gives us a positive 1/2. And then we flip and multiply by our exponent, so we get 2 over 1, which is just 2. And then plus c. And we need to do one more step. We need to back sub. So we need 2 times 2x squared minus x plus 7, all to the 1/2, plus c. And then you could also rewrite this as the square root if you wanted to, but leaving it as to the exponent of 1/2 means the same thing. But here we have our final answer. All right, so for part D, we have a definite integral. Okay, so let's go ahead and see where this takes us. So we want u to be our natural log of x. All right, we did a similar problem already. So we know that when we take the derivative of u, it's going to give us our 1 over x, which we already have in our problem. So that works out. And so we have du is equal to 1 over x dx. All right, so we have our du is here. And this is our u. The 2 is a constant. It's fine that it's still there. All right, so we end up with this is equal to 1 up to e of 2u du. All right. So we could pull the constant out if we'd like. We can also think one step ahead and notice when we do our power rule, it's going to become u squared and then divided by 2. So our 2's will cancel out. All right. So we get u squared evaluated from 1 to e. Now remember, we don't need to include our plus c when we're dealing with a definite integral. Our plus c is only with indefinite integrals. All right. The next thing we need to notice is that we can't immediately evaluate at our bounds. And why is that? 1 and e are bounds for the variable x. Because there's no x currently here, we cannot plug e and 1 into our function because they're bounds for the wrong variable. All right? Not for u. So we have two different ways that we can handle a definite integral when we're dealing with u substitution. All right, so we have two ways to handle this. So let's look at way one, so the first way. All right, so we still have our u squared from 1 up to e. All right, the first way is simply leave the bounds how they are and do your back substitution, so back sub, before plugging in your bounds. So we said u was equal to the natural log of x. So we just need to plug in the natural log of x squared evaluated from 1 to e. Okay? So we can go ahead and plug in our bounds now because they were bounds for x. And now we have the variable x. So we can go ahead and plug them in. So we get the natural log of e squared minus the natural log of 1 squared. So we get 1 squared minus 0 squared, which is 1. Okay? Our second way is we can actually switch the bounds. So way one, leave bounds and back sub first. Way two is switch the bounds. Nope. Switch the bounds and don't back sub. So we had 1 and e for x. Now we just need to find out what are the bounds for u. Okay? So we know that u is equal to the natural log of x because that's what we chose it to be at the very start of this problem. So let's first look at the lower bound. For the lower bound, we were given that x is equal to 1. So if we want to find the value for u at x is equal to 1, we can plug this in to our equation for u. So this is the natural log of 1. So that is 0. Okay, so our new lower bound is u is equal to 0. That's a 0. There we go. And for our upper bound, we have x is equal to e. So we want to find the u value when x is equal to e, which is 1. So our new upper bound is u is equal to 1. All right. So we can start with u squared evaluated from 1 to e, and we can switch the bounds. We can switch the bounds. All right. So now we have u squared evaluated from 0 up to 1. These are now the bounds for u instead of the bounds for x. So we can plug them directly in, and we can get 1 squared minus 0 squared, which is 1. All right, so we see that both ways give us the same answer. All right, but the first way you have to remember to back sub first before you start plugging your variables in. The other way, you can choose to find your new lower bounds and upper bound at the very beginning of the problem. That way you don't have to remember to back sub first. So both have their pros and cons. It's a complete personal preference on which way you would like to handle your definite integrals using a u substitution. So pick whichever way you feel most comfortable with. All right. So let's get on to example E, where we have another definite integral. Okay, so we want to pick u to be our exponent. So we have negative x squared. Then we need to take this derivative. We get du over dx is equal to negative 2x. And then we get du is equal to negative 2x dx. So if we notice, we do not have a negative 2 in our original function. That is totally fine. The way we're going to handle that is we're going to divide it out. Okay, so we're going to divide over here by negative 2. So we get negative 1/2 du is equal to x dx. So now we need to substitute negative 1/2 du for our x dx. All right, we need to include this negative 1/2 in there. And then our u is our negative x squared. So what we're going to end up with is the integral from 0 to 1 of negative 1/2 e to the u du. Okay? So we can go ahead and take this integral, which we know is just going to be negative 1/2 e to the u, because our constants come in and out of integration, and the integral of e to the u is simply e to the u. But it needs to be evaluated from 0 to 1. So we have our options. We can decide to back sub and then plug our bounds in, or we can switch our bounds. I'm going to go ahead and pick way 1. So I'm going to pick way 1, where we're going to back sub first. So we want to back sub. Again, you can pick either option here. So we have negative 1/2 e to the negative x squared, evaluated from 0 to 1. And so we have negative 1/2 e to the negative 1 plus 1/2 e to the 0. And so we just end up with negative 1/2 e to the negative 1 plus 1/2. E to the 0 is just 1. And we can leave it at this. Okay? So if the computer asks you to type in the exact answer, you would type in the value e instead of the approximate decimal value. All right, let's keep going. So we want to look at example 3. And here we're told that we need to find this integral in 2 different ways. Part 1, the first way is part A, and we need to expand the integrand using distribution and then take the integral. So remember when we had that binomial to the 9th power, and I was like, go for it if you feel like it? Well, in this case, it's a little bit more feasible to go through and multiply everything out. So if we want to take our integral from 2x times x squared plus 4 dx, we can go ahead and multiply it out. So we have 2x cubed plus 8x dx. Well, this way we just have 2 different power rules that we need to use, and we can take this integral pretty simply, right? So we'll end up with x to the 4th, 2 over 4, plus x squared, 8 over 2, plus c. If we simplify this, we get 1/2 x to the 4th plus 4x squared plus c. Okay? So that's how we can take that integral using distribution. But we could also use substitution. Either way will work. So if we want to use substitution, let's let u be equal to our binomial, so x squared plus 4. So then if we take the derivative, we have our 2x that we need. So then we have du is equal to 2x dx. And we can go ahead and plug this into our integral. So we just have u du. Okay? So let's go ahead and calculate this. This is just going to be u squared over 2. We can't forget our constant. Okay? And then we need to plug back in our original variable. So we need to back sub. So we get x squared plus 4 squared over 2 plus c. Okay. Now at first you might think these don't look like the same answer. All right. Let's go ahead and continue multiplying out our current work to see what we end up with. Okay. So if we FOIL out the top, I'm just going to bring the 1/2 out front here. We will end up with x to the 4th plus 8x squared plus 8 plus our constant c. And then if we multiply through by our 1/2, we end up with 1/2 x to the 4th plus 4x squared plus 4 plus c. All right, and so here is this answer. So let's see, can I scroll up? Let's go ahead and take a look at both of our answers here. Each of them have 1/2 x to the 4th plus 4x squared plus c. The only thing that differs is our u substitution answer has a plus 4. Are they both correct? Well, remember, this is an antiderivative. So if we took the derivative of each of these answers, we would hope to get back the original function, right? And if you take the derivative of both of these, they will both be the same because our extra plus 4 down here, well, the derivative of that is 0. Same thing with our c. Okay? So while they may look different, and they are by a constant factor of 4, okay, they're still both correct. And if we were to find the actual value for c and do the math necessary for that, we would end up with 2 identical answers. All right, in any event, both ways are completely valid, and if you don't need to use substitution and you can go ahead and multiply it through, you're always more than welcome to do so. Well, part C was explain how they're different and if they're both correct, and we just did that verbally. Okay? So let's look at example 4. A coal miner has a mine that has 200 tons of coal in it. In the year 2019, he begins to mine the coal at a rate given by this R of t function. And t is the amount of years since 2019. So we need to assume that he continues mining at the same rate every year. And we need to write an expression for the total amount of coal mined t years after 2019. All right, so the total amount of coal would be our total accumulated change, meaning we need an integral. Okay, we need an integral, and we need to integrate the rate. So our rate is 0.8 times e to the 0.0075t. Cap it off with a dt. And we need some bounds for this integral. So we want to know the total amount of coal mined t years after 2019. So it says that he began mining in 2019. So if t is the number of years since, if we started 2019, it's been 0 years since the start of 2019, right? So we're going to start at 0. And normally, if we're asked to find the total amount of something between the first 2 years, right, we would then say, well, t has to be equal to 2, and so we'd put a 2 up here. However, we were just asked for the total amount of coal mined t years. We weren't given an exact number of years, but that is okay. We are allowed to put a variable in the bounds of an integral. So we're allowed to put t up here as our upper bound. That way, when we evaluate this, we have a function where we can plug in the value and we can get out the total amount of coal for that many years. All right. So part A was just asking us to put together the expression. All right, part B is actually going to ask us to use that expression. So when is the miner predicted to have mined all the coal in his mine? So that means we want this integral to be equal to the total amount of coal in the mine. All right, so we want 200 tons of coal to be equal to this integral from 0 up to t of 0.8 e to the 0.0075 t dt. All right, so when this total amount of coal mined is equal to 200, well, that is when the coal has then finally run out, or the mine has finally run out of coal, right? So let's go ahead and take this integral. So we're going to end up with e to the 0.0075 t, and then divide that by the constant in the exponent, so our 0.0075. And we had the 0.8 already there, we can't forget about, evaluated from 0 up to t. Okay. So this 0.8 divided by 0.0075 gives us 106.66 times e to the 0.0075 t, still evaluated from 0 to t. Okay. So let's plug in our top bound. So when we plug in t, really nothing changes. We end up with our constant here times e to our 0.0075. Well, we just plug in a t where we see a t. So that's what I mean by nothing changes. And then minus, when we evaluate at 0, we get our constant, 106.66, e to our 0.0075 times 0, which is just 0. And we know that e to the 0 is 1. So we end up with 106.66 e to the 0.0075 t minus just our constant here. So we evaluated that integral, but remember we were setting it equal to 200. So we have this set equal to 200, and the question was, how long is it going to take for him to mine all the coal in his mine? So we need to solve for the time. We need to solve for the variable t. All right, so we can go ahead and add 106.66 to both sides. We get 306.66 is equal to 106.66 e to the 0.0075 t. Go ahead and divide both sides by our 106.66, and we get 2.875 is equal to e to the 0.0075 t. And then remember what we need to do when we have a variable in an exponent is we need to take the natural log. All right, so we take the natural log of both sides. Natural log of both sides. And that lets us bring our exponent out in front, right? So the left-hand side evaluates to 1.056, and the right-hand side we get 0.0075t. We'd be left with natural log of e, but that's just 1, right? So we don't need to write that. Then we finally divide by our constant in front of t, and we end up with t is equal to 140.815. All right, so the coal mine will be empty in 140 years. Approximately 140 years. Okay, and if you wanted to double check your answer, if we can double check, all right, by taking our integral from 0 up to our t value that we were interested in, which is 140, all right, of our 0.8 e to the 0.0075t dt, and I just plug this into a calculator, and you end up with 200 tons, which was the total amount of coal that we started with in the mine. So it does check out that it's going to take 140 years to finish mining all the coal. All right, I know I said this was going to be a long one. I promise this is our last example. Okay, so we have a bacteria population that starts with 600 bacteria and grows at a rate given here. How many bacteria will there be after 2 hours? All right, so we need to set up our integral equation. So we take the integral from 0 up to t, which is 2 hours. So 0 up to 2 of our rate. So our rate is 650 e to the 1.125 t. Can't forget our dt. Okay. So to take this integral, we have e to the 1.125 t divided by that constant, 1.125, and then we have our 650 that was still there, and we need to evaluate this from 0 to 2. We can go ahead and simplify by doing this division here, so we end up with 577.77 e to the 1.125 t evaluated from 0 to 2. All right, so then we plug in our top bound first. So we get 577.77 e to the 1.125 times 2 minus our 577.77 e to the 1.125 times 0, which is just 0, and e to the 0 is 1, right? All right. So finally, we get 4,903.96. Okay. But what was the question asking? We were asked how much bacteria will there be after 2 hours? What we just calculated is the total amount of change in the first 2 hours. But we need to add that to what we started with. All right, so started at 600 bacteria. Population increased by this 4,903.96. So the total population after 2 hours is the sum of the two, which is 5,503.96 bacteria. And as promised, that is our last example, and this is our last lecture. So please don't forget to take your one last comprehension quiz. Start studying for your final exam. If you have any questions, please send me an email. It has been a pleasure. Have a good rest of your summer.